the lecture will be recorded, so then it will be possible to use this lecture as a record from the web page. So today is the third lecture, which will be given by Sergey, and it is his second lecture, which will be given from China. So the floor is yours, Sergey, please.
Thank you very much for the introduction. The title of my lecture is Possible Analogues of the Hilton Milner theorem for Paley graphs of square order and Peis graphs, and it is a natural continuation of the previous two lectures. Let us start. Akademgorodok conjectured that the largest one-intersecting system that was not a subset of the canonical intersecting set system is the set of all k subsets that contain at least two elements from a fixed set of three elements. It turns out that this conjecture is not true. The actual maximum sets were given by Hilton and Milner. Hilton and Milner proved that the largest intersecting system that is not a subset of a canonical intersecting system can be constructed as follows. Let F0 be the set system of all k sets that contain the element 1, and let A be the set 2, 3, so on, k plus 1. Define F prime to be the system of all the sets in F0 that intersect A together with the set A. This system is intersecting and has size given on the slide. The next result is known as the Hilton Milner theorem, proved in 1967. Let k and n be positive integers with the property that k is between 2 and n over 2 inclusive. Let A be an intersecting k system on an n set such that the intersection of all the sets in this system is empty. Then the size of A is bounded by this number, which is the same as the number on the previous slide. Moreover, for k greater than 3, equality holds if and only if A is isomorphic to the system of all sets in F0 that intersect the set 2, 3, so on, k plus 1, together with the set together with this set 2, 3, so on, k plus 1. For k equals 3, there are two non-isomorphic systems that meet this bound, the one described above and one more. Let us give some comments. Similar to the Akademgorodok theorem, the Hilton-Milner theorem has two parts, a bound and a characterization of families that meet the bound. In other words, the Hilton-Milner theorem shows what is the second largest size of a maximal intersecting family, maximal with respect to inclusion, and gives their characterization. In terms of graphs, this theorem gives a characterization of second largest maximal co-cliques in the Kneze graph k of nk, or equivalently second largest maximal cliques in the complement of the Kneze graph. In terms of the complement of this Kneze graph, k of nk, where k is between 2 and n over 2 inclusive, the general second largest clique can be constructed as follows. Take a canonical clique C, take a vertex x outside of C, let Cx be the set of neighbors of x in C, then the second largest clique is Cx, join it with the set consisting of x. And let us formulate our first problem in this lecture. Whenever an analog of the Erdős-Korada theorem is proved for some family of graphs, investigate whether there holds an analog of the Hilton Milner theorem, that is, determine the size of the second largest maximal cliques, if there are any, and characterize them. We say that an analog of the Hilton Milner theorem is exact if the structure of the second largest maximal cliques relies on the structure of the general second largest family of the intersecting sets, that is, a vertex X outside of a canonical clique C joined with its neighbors Cx in C. In this lecture, we discuss two conjectures verified for small values of parameters for Paley graphs of square order and a subclass of Peis graphs, and we also discuss why their statements of the statements of these conjectures can be viewed as exact analogues of the Hilton Milner theorem. In 1996, Baker et al. Initiated a study of second largest maximal cliques in Paley graphs of square order. Let us introduce some notation. Given an odd prime power q, put R of q to be the remainder after division q by 4. So if q is congruent to 1 modulo 4, then R of q is 1, and if q is congruent to 3 modulo 4, then R of q is 3. In particular, in that paper, in the mentioned paper, the following construction of maximal cliques of size q plus R of q over 2 in Paley graph of square order P of q squared was proposed. Let beta be a primitive element in a finite field fq squared, where q is a node prime. Further, let epsilon be beta to the power of q plus 1 over 2, and S be the set of all neighbors of the set of all neighbors of epsilon in the subfield fq. The following theorem was proved. If q is congruent to 1 modulo 4, then S joined with the set consisting of epsilon is a maximal clique in P of q squared of size q plus 1 over 2. And if q is congruent to 3 modulo 4, then S joined with the set consisting of epsilon and minus epsilon is a maximal clique in P of q squared of size q plus 3 over 2. So they found maximal cliques of order q plus of size q plus R of q over 2. However, their extensive searching for the values u less or equal to 25 showed that these are not the only maximal cliques of such size under the action of the full automorphism group of Paley graphs. However, they conjectured for an odd prime power q greater or equal to 5, the maximal cliques of size q plus R of q over 2 in the Paley graph P of q squared are second largest. In other words, there are no maximal cliques of size S in P of q squared, where S is strictly between q plus R of q over 2 and q. This conjecture gives a reasonable bound for the size of second largest maximal cliques. In this lecture, we discuss our recent developments related to this conjecture. Although the conjecture has not been confirmed yet, we were able to realize new interesting details and formulate a stronger conjecture whose statement is an exact analog of the Hilton Milner theorem. Our entry point to the project on maximal cliques in Paley graphs of square order was the project on determining eigenfunctions of distance regular graphs having minimum cardinality of support. This project was proposed by Denis Krotov. His former PhD student Alexander Volozhenich made significant contribution to the latter project. You can see a nice survey for more details, and Alexander initiated investigation of eigenfunctions of Paley graphs of square order having minimum cardinality of support. Let gamma be a k-regular graph on n vertices and theta be an eigenvalue of its adjacency matrix A. Let U be a column eigenvector of A corresponding to theta. Then U defines a function fu from the set of vertices V to the field of real numbers, which is called a theta eigenfunction of gamma. For an eigenfunction fu of gamma, the support is the set of all vertices in the graph such that the value of this function is not equal to 0. Let us formulate two problems related to the minimum cardinality of supports of graphs, of eigenfunctions of graphs. Given a graph gamma and its eigenvalue theta, find the minimum cardinality of the support of a theta eigenfunction of gamma. This problem is called the MS problem. A theta eigenfunction having the minimum cardinality of support is called optimal. And a stronger problem is as follows. Given a graph gamma and its eigenvalue theta, characterize optimal theta eigenfunctions of gamma. The following, let us discuss a bound, a lower bound on the number or on the cardinality of support. Let gamma be a distance regular graph of diameter d of gamma with intersection array. For each distance regular graph gamma, we can have such an array. It has exactly 2d numbers. For an eigenvalue theta of gamma, the following bound was proposed by Krotov, Mogilnik, and Potapov in 2016. This bound is called the weight distribution bound. A theta eigenfunction f of gamma has at least so many non-zeros. This is the sum from I equals 0 to d, sorry, not of g, but d of gamma. And the term is the absolute value of wi, where w0 is 1, w1 is theta, and further values of wi can be obtained by using this recurrence relation. This recurrence relation involves the eigenvalue theta and the constants from the intersection array of this distance regular graph. It was also shown in that paper that for the smallest eigenvalue of a distance regular graph gamma, the tightness of the weight distribution bound implies the existence of an isometric bipartite distance regular induced subgraph T0 union T1, where T0 and T1 are parts, such that an optimal eigenfunction up to multiplication by a non-zero constant has the following form. F of x is equal to 1 if x belongs to T0, f of x is equal to -1 if x belongs to T1, and it equals 0 otherwise. It was also shown that if gamma has a Delsart clique and each edge of gamma lies in a constant number of Delsart cliques, then the converse is true, that is, the existence of an isometric bipartite distance regular induced subgraph T0 union T1 implies tightness of the weight distribution bound and existence of an optimal eigenfunction of the same form that is above. If gamma is a stronger regular graph with non-principal eigenvalues R and S, where S is negative and R is positive, then the following corollary holds. An S eigenfunction f of gamma has at least minus 2s non-zeros. Moreover, if the size of the support of f meets the weight distribution bound, then there exists an induced complete bipartite subgraph with parts T0 and T1 of size minus s. In view of the property that taking the complement in a stronger regular graph swaps the eigenspaces of these two graphs in some way, we can apply this for the positive. We can apply this for the positive eigenvalue R, and we have the following statement, item 2. An R eigenfunction f of gamma has at least 2 times R plus 1 non-zeros. Moreover, if the size of the support of f meets the bound, it's missed here, then there exists an induced pair of isolated cliques T0 and T1 of size R plus 1. Again, if gamma has a Delsart clique and each edge lies in a constant number of Delsart cliques, then each induced complete bipartite subgraph with parts of size minus s gives rise to an optimal S eigenfunction whose size of support meets the weight distribution bound.
Sergey, excuse me, could you please show the previous slide? But is it possible that there are more than 2? More than 2 cliques in the graph. So it is not necessary that there are only 2 cliques, right? Yeah.
Yeah, right. So, but you mean item 2, right?
Right. Yeah. Item 2. Yeah. Right. Yeah.
Yeah. It says that if the bound is tight, if the weight distribution bound is tight for the positive eigenvalue R of a stronger regular graph gamma, then then there necessarily exists an induced pair of isolated cliques of size R plus 1. And there may be more than one such pair, of course.
Yeah, right.
Okay.
Yes, okay. But I have also a further question. So in this corollary, you don't state any connection between the support of F and bipartite subgraph or isolated cliques, but are they the same? The support coincides with the union?
Yeah. This is a corollary of this slide, actually, not of the statement on this slide.
I see.
T0 and T1 are the parts of that bipartite distance regular induced subgraph. And in the case of stronger regular graph, this bipartite graph becomes a complete bipartite graph. And everything is just the same. So applied to stronger regular graphs, this statement becomes more clear and strong. Because it applies
but even on this slide, Okay. If further for. Okay. Optimal eigenfunction is always of this form. I see. So you just specialize this.
Yeah. If the weight distribution bound is tight,
yeah.
Then an optimal eigenfunction necessarily has this form.
Yeah. Okay. Thank you. It's now clear.
Okay. In 2018, together with my co-authors, we showed the tightness of the weight distribution bound for both non-principal eigenvalues of Paley graphs of square order. The eigenvalues are -1 minus q over 2 and -1 plus q over 2. And our proof was based on the subgroup of order q plus 1 in the multiplicative group. Let me provide the details. Let beta be a primitive element in the field fq squared. Let omega be beta to the power of q minus 1. Then the subgroup generated by omega is the subgroup of order q plus 1 in the multiplicative group of this field. And two important things can be said about Q. First, Q is an oval in the corresponding affine plane that is a set of points of size Q plus 1 such that no three of them lie on a line. And second, Q is the kernel of the norm mapping N over the subfield of Q, which means that Q is the set of all elements gamma from the multiplicative group of the field fq squared, such that gamma to the power of q plus 1 equals 1. Or equivalently, q is equal to x plus y alpha. Q is equal to the set of all elements x plus y alpha, where x and y run over fq, and x squared minus y squared d equals 1, where d is a non-square in fq star and alpha squared equals d. So the point is that Q has a multiplicative description as well as an additive description, two kinds of algebraic description. Let Q0 be the subgroup of index 2 in Q, and Q1 the non-trivial coset. Then the following was proved in our paper. If Q is congruent to 1 modulo 4, then Q induces a complete bipartite graph with parts Q0 and Q1. If Q is congruent to 3 modulo 4, then Q induces a pair of isolated cliques Q0 and Q1. And the size of these parts Q0 and Q1 is just as required by the weight distribution bound applied to stronger regular graphs. Since Paley graphs of square order do have Delsart cliques, we know that there are only canonical cliques, and every edge lies in exactly one Delsart clique. We have the following corollary: the weight distribution bound is tight for both non-principal eigenvalues of Paley graphs of square order. So we have the following construction of such an eigenfunction. It has value 1 on Q0, it has value -1 on Q1, and it has value 0 otherwise.
Yeah, Sergey, I have another question on corollary 2. So how about the proof of corollary 2? Seems you say you can prove corollary 2 because of the existence of Delsart clique.
Actually, we gave an explicit proof. we gave an we considered the oval and the lines by hands and show it it explicitly, but it can
So in some sense, so the existence of the del-Sol clique gives a somehow conceptual proof, but you can prove it directly by computation, right?
Yes.
Yeah, okay, thanks.
Knowing the structure of Q, we were also able to construct new maximal cliques of the second largest known size, that is Q plus R of Q over 2 in Paley graphs of square order P of Q squared. And we had the following statement, the following theorem: if Q is congruent to 1 modulo 4, then Q0 and Q1 induce maximal co-cliques of size Q plus 1 over 2 in P of Q squared. That is, Q0 and Q1 induce maximal cliques of the same size Q plus 1 over 2 in the complement of P of Q squared, which is known to be isomorphic to the original Paley graph. If Q is congruent to 3 modulo 4, then Q0 and Q1 joined with the 0 element each induce maximal cliques of size Q plus 3 over 2 in P of Q squared. The full automorphism group of a Paley graph of square order is known to preserve the lines in the corresponding affine plane. This shows that our maximal cliques are not equivalent under the full automorphism group of the graph, are not equivalent to the cliques constructed by Baker et al. Indeed, in our construction based on the oval Q, almost all triples of vertices of the clique are not collinear, because most of the vertices belong to an oval. On the other hand, almost all triples of vertices of the clique from Baker et al.'s construction are collinear. As you remember, the construction is that we take the subfield FQ, the element epsilon outside of the FQ, and consider its neighbors in FQ. So most of the elements, all the elements of Baker of the cliques from Baker et al. Construction belong to the subfield FQ, all but one or two, depending on the congruence of Q modulo 4. So for sure, we have constructed non-equivalent maximal cliques of the same size under the action of the full automorphism group of Paley graphs of square order. We also made some computations. If Q is equal to 9, 11, 13, 17, 19, and 23, then Paley graphs of square order of this of order Q squared indeed have extra maximal cliques of this size Q plus R of Q over 2, and this confirms the statement. This confirms the results of the experiments made by Baker et al., but they stopped at the value Q equals 25. But we continued the search, and whenever Q is between 25 and 83, our computations showed that the Paley graph P of Q squared contains exactly two non-equivalent under the action of the full automorphism group maximal cliques of size Q plus R of Q over 2. We thus formulate the following conjecture. For Q greater or equal to 25, the graph P of Q squared contains exactly two non-equivalent under the action of the full automorphism group maximal cliques of size Q plus R of Q over 2, and these cliques are second largest. the automorphism group of Paley graph of square order P of Q squared acts arc-transitively, and the following equality holds. The automorphism group consists of all mappings V to AV gamma plus B, where A is a non-zero square, B is an element or is just an element, any element of the field, and gamma represents a field automorphism. This automorphism group preserves the sets of quadratic and non-quadratic lines and acts on each of them transitively. We also know that this group has a subgroup that stabilizes the quadratic line FQ and acts faithfully on the set of points that do not belong to FQ. This subgroup is given by the affine transformations x to ax plus b, where a is a non-zero element from the subfield FQ, and b is just any element of FQ. Let us check that the sizes, at least the sizes, coincide. There are q minus 1 times q such mappings, and there are q squared minus q points that do not lie on the line FQ. So the sizes are the same, and it can be quite easily checked that it acts faithfully on the set of points that do not this group stabilizes the quadratic line FQ and acts faithfully on the set of points that do not belong to FQ.
Excuse me, what is a quadratic line and non-quadratic line?
Okay, it was said in the first lecture. So
can you briefly recall?
Yeah, let me briefly recall.
Yeah.
If we have two elements of a finite field FQ squared such that their difference is a square, then let us look at them as at points of the corresponding affine geometry and consider the line through this point. Then the difference between any two points from this line is also a square. So we call such a line a square, and this line is actually a canonical clique in the Paley graph. But if we take two points with whose difference is non-square, then for any two points from this line, we have the same statement. The difference is a non-square, and we call such lines non-quadratic. And in general, for Paley graphs of square order, two elements are adjacent if and only if the line through this element is quadratic.
Yeah. Okay, thank you. So that these two different kinds of lines are formulated by Blockhaus.
Yeah, exactly.
Yeah, thanks.
Let us give a general geometric structure of maximal cliques from the construction of Baker et al. Take an element gamma from FQ squared minus FQ. Since FQ is a quadratic line, the line through gamma that is parallel to FQ is quadratic too. The other q minus 1 over 2 quadratic lines through gamma, and there are q plus 1 lines through gamma in total. Q plus 1 over 2 of them are quadratic. Q plus 1 over 2 of them are non-quadratic. We consider all the quadratic lines through gamma. One of them is parallel to FQ, and the other q minus 1 over 2 quadratic lines through gamma intersect FQ in Q minus 1 over 2 points denote this set of Q minus 1 over 2 intersection points by X gamma. For the conjugate, it can be shown that for the conjugate element gamma bar, the equality X gamma bar equals X gamma holds. And the situation is that if Q is congruent to 1 modulo 4, each of the sets gamma union, the set consisting of gamma union X gamma and the set consisting of gamma bar union X gamma induce a maximal clique of size Q plus 1 over 2. And if Q is congruent to 3 modulo 4, then the set consisting the union of two sets, the first consisting of gamma and gamma bar, and the second X gamma. So this united set induces a maximal clique of size Q plus 3 over 2. So we just mentioned these properties of the automorphism group of Paley graphs of square order. This preserves the set of quadratic lines. So in the case of construction by Baker and al., they can, in this sense, they consider it a special quadratic line and a special point that is not on this special quadratic line, and show it that this gives a maximal clique. But using these properties of the full automorphism, these properties of the automorphism group of Paley graph of square order, we can conclude that actually the quadratic line can be chosen as we want. Any can be chosen to be any, and the point that does not belong to this line can also be chosen to be any. And if we have, this slide we have just discussed is devoted to the case when the quadratic line is still FQ, but the point that is not on the line, it can be any. And in the case of the construction, original construction by Baker et al., their line was the imaginary line, the analog of the imaginary. They took a special point from the analog of the imaginary line in the affine plane. But we can take any of them. We can any point that it does not belong to this line, and in their case, the points outside were epsilon and minus epsilon. In particular, they were conjugate. But if we take any point gamma that does not belong to FQ, then we can do just the same. The only difference is that we replace the notation epsilon and minus epsilon with the notation gamma and gamma conjugate. So the general geometric, in view of this, a general description of maximal cliques proposed by Baker et al. Is as follows. Take a quadratic line C, that is a canonical clique in the Paley graph of square order. Take a vertex X outside of C. Let Cx be the set of neighbors of X in C. Then there exists a uniquely determined vertex X prime outside of C such that X is not equal to X prime, but Cx prime, the sets of neighbors in C, Cx prime and Cx are equal. Then X union Cx and X prime union Cx are cliques. Moreover, if Q is congruent to 1 modulo 4, then these cliques are maximal of size Q plus 1 over 2. If Q is congruent to 3 modulo 4, then these cliques are not maximal, but their union X prime the set consisting of x and x prime union Cx is a maximal clique of size q plus 3 over 2. Thus, if q is congruent to 1 modulo 4, we have the same structure of the maximal clique as in the Hilton Milner theorem. If q is congruent to 3 modulo 4, the structure of the maximal clique relies on the structure of the maximal clique from the Hilton Milner theorem. So we have an extra vertex comparing with the original Hilton Milner theorem. The only thing needed to regard conjecture 2 as an exact analog of the Hilton Milner theorem is to show that the two known constructions are equivalent, even if they are not equivalent under the action of the full automorphism group of Paley graphs of square order. Such an equivalence indeed exists, and we further discuss it in details. To introduce the equivalence, let us reinterpret the two known constructions of maximal cliques of size q plus r of q over 2 in Paley graph of square order p of q squared. For each of the two constructions, the first given by Baker et al., and the second is given in our paper published in 2018. For each of these two constructions, we will consider two important incarnations. The required equivalence can be understood for the resulting four instances. Recall that we view fq squared as a vector space over fq generated by the elements 1 and alpha, where alpha squared is d and d is a non-square in the multiplicative group fq star. So-called fq alpha construction, almost the same as what Baker et al. Proposed. Let us consider the quadratic line fq, the point alpha that does not belong to fq, and the pencil of quadratic lines through alpha. Each line of the pencil except c plus alpha, except the line consisting of elements c plus alpha, where c runs over fq, intersects fq at a point, denoted by c1, so on, cq minus 1 over 2, all the intersection points. So the set alpha, c1, so on, q minus 1 over 2 is a clique of size q plus 1 over 2 in Paley graph of square order, in the Paley graph p of q squared. The points minus alpha and alpha have the same neighbors in fq. Therefore, the same set with alpha replaced by minus alpha is also a clique. The first and the second cliques are equivalent under the field automorphism gamma to the power of q, that is, which is an analog of the complex conjugation, and this conjugation acts as alpha to minus alpha and ck to ck for any k. For q congruent to 3 modulo 4, the line consisting of elements c alpha, where c runs over fq, so this line is the analog of the imaginary x, imaginary line in the Euclidean in the complex plane generated by the number I. So this line in our case contains minus alpha and alpha, and it is known that alpha is a square if and only if q is congruent to 3 modulo 4. This means that this line, this imaginary line, is quadratic if q is congruent to 3 modulo 4 and is non-quadratic if q is congruent to 1 modulo 4. Hence, in the case q is congruent to 3 modulo 4, the two cliques alpha C1 so on CQ minus 1 over 2 and minus alpha C1 so on CQ minus 1 over 2 are combined into one. And we have the following theorem. If just a reinterpretation of the theory of the construction by Baker et al. If Q is congruent to 1 modulo 4, then alpha C1 so on CQ minus 1 over 2 is a maximal clique of size Q plus 1 over 2 in P of Q squared. If Q is congruent to 3 modulo 4, then plus minus alpha C1 so on CQ minus 1 over 2 is a maximal clique of size Q plus 3 over 2 in P of Q squared. Then let us consider a very similar situation, but a bit different. The second interpretation of the construction of the general construction by Baker et al. Uses the imaginary line alpha fq and the point 1 that does not belong to this imaginary line. For Q congruent to 1 modulo 4, respectively Q congruent to 3 modulo 4, consider the pencil of non-quadratic, respectively quadratic lines through 1. They all, except the line 1 plus C alpha, the line that passes through 1 and that is parallel to imaginary line, all such lines intersect alpha fq, and there are q minus 1 over 2 of them. So if q is congruent to 1 modulo 4, we consider the pencil of non-quadratic lines through 1. If q is congruent to 3 modulo 4, we consider the pencil of quadratic lines through 1. In each case, there are q minus 1 over 2 of them, because we know that the imaginary line is quadratic if and only if q is congruent to 3 modulo 4. And denote the intersection points by C1 alpha, so on CQ minus 1 over 2 alpha. The elements minus 1 and 1 have the same neighbors in the imaginary line. Thus, 1 together with the intersection points and minus 1 together with the intersection points are co-cliques when Q is congruent to 1 modulo 4, and cliques when Q is congruent to 3 modulo 4 of size Q plus 1 over 2 in P of Q squared. And they are equivalent under this automorphism. And if Q is congruent to 3 modulo 4, these two objects, either co-cliques or cliques, depending on the congruence of 3 modulo 4, are combined into one. So we have the following statement. If Q is congruent to 1 modulo 4, then 1 together with the intersection points is a maximal independent set, maximal co-clique of size Q plus 1 over 2 in P of Q squared. If Q is congruent to 3 modulo 4, then plus minus 1 together with the intersection points is a maximal clique of size Q plus 3 over 2 in P of Q squared. So we have considered two important incarnations of the general construction by Baker et al. Note that the sets from theorem 7...
Sergey, excuse me. Would you please show the previous slide? How did you find this maximal independent set?
It follows from the... I mean, Baker et al. Didn't use the geometric language too much. But if we apply the full automorphism group of Paley graphs of square order, then we can have a general construction inspired by their construction. We can have a general construction in terms of a canonical Descartes clique and a point that does not belong to this line. So in these two cases, FQ alpha construction and alpha FQ1 construction, we just mimic Baker et al.'s construction and consider some specific line and some specific point that does not belong to this line. So we just apply, we just consider two very special cases of the general construction inspired by the original construction by Baker et al.
I see. I see. Okay, thank you.
Yeah, I think what Elena wants to know is just simple observation that if you have a clique and if you multiply everything by alpha, which is a non-square, then you get a co-clique. Is that right?
Yeah, yeah. Alpha can be alpha is a non-square in the case when Q is congruent to 3 modulo 4, is congruent to 1 modulo 4, and alpha is a square when Q is congruent to 3 modulo 4. So so the purpose of this consideration is as follows. In the original construction by Baker et al., with no dependence on the congruence of Q modular 4, they always obtained maximal cliques, not co-cliques. But in our construction based on the oval, in one case we obtained co-cliques, and we were needed to go to the complement to get cliques. But in the other case, we obtained a clique. The advantage of this alpha FQ1 construction that can be obtained from the original construction from FQ alpha construction by multiplication by alpha, just as you noted, the advantage is that it possesses the similarity with the construction based on the oval. In the case of Q is when Q is congruent to 1 modulo 4, we get co-cliques. In the case of when Q is congruent to 3 modulo 4, we get cliques.
In the middle of the slide, you have respectively cliques, but what does this respectively refer?
It starts from the beginning.
Okay. So it comes from that.
Yeah, Q is congruent to 1 modulo 4, or Q is congruent to 3 modulo 4. And whenever we write respectively, we just refer to the case Q is congruent to 3 modulo 4.
I see. Okay. Yeah, thanks.
So this interpretation, the advantage of this alpha FQ1 construction is that it has this kind of similarity with the construction based on the oval. Note that the sets from theorem 7 are obtained from the sets from theorem 6 by mapping gamma to alpha gamma, which is an isomorphism with the complement P of Q squared when Q is congruent to 1 modulo 4, and an automorphism of P of Q squared when Q is congruent to 3 modulo 4. This is just what you said. Q construction. Let us, as we promised, we consider two cases of the general construction by Baker et al., two special cases, and we will consider two special cases of the construction based on an oval. So then we will have 4 special cases, and we will establish correspondences between we will have matching between the set of first 2 cases and the set of second 2 cases. Let us repeat the construction based on the oval. Let beta be a primitive element in FQ squared and omega be beta to the power of Q minus 1. Then omega is a square in FQ squared star, and omega and the subgroup generated by omega is a subgroup of order q plus 1 in fq squared star, denote it by q. On the other hand, the kernel of the norm mapping is also a subgroup of order. Okay, we can skip it a bit. So the kernel and q just coincide. We noticed it already. And the points of q form an oval in the affine geometry. We have the sets q0 and q1, two parts of q. q0 is the subgroup of index 2 in q, and q1 is the unique non-trivial coset. And the construction was as follows: theorem 8, let us repeat it. If q is congruent to 1 modulo 4, then q0 and q1 are maximal co-cliques of size q plus 1 over 2 in p of q squared. And if q is congruent to 3 modulo 4, then q0 union 0 and q1 union 0 are maximal cliques of size q plus 3 over 2 in p of q squared. And again, if we multiply everything in the q construction by alpha, we also get something. The following construction is a corollary of theorem 8 and the fact that the multiplication by alpha is an isomorphism with the complement when q is congruent to 1 modulo 4, and an automorphism of p of q squared when q is congruent to 3 modulo 4. We have the following: if q is congruent to 1 modulo 4, then alpha q0 and alpha q1 are maximal cliques of size of q plus 1 over 2 in p of q squared. If q is congruent to 3 modulo 4, then alpha q0 union 0 and alpha q1 union 0 are maximal cliques of size q plus 3 over 2 in p of q squared. In this fourth case, you can see that we have in this q construction multiplied by alpha, we have the same kind of similarity with the original construction by Baker et al. In both cases, q is congruent to 1 modulo 4 and q is congruent to 3 modulo 4. We have cliques, not a co-clique and clique. Further, we introduce two linear fractional mappings which establish correspondences between the sets from theorems 8 and 7 and between the sets from theorems 9 and 6. Let us introduce a mapping phi. Let us define the first mapping phi by the following rule: phi of gamma equals gamma plus 1 over gamma minus 1 if gamma is not equal to 1, and phi of gamma is equal to 1 if gamma equals 1. Lemma 1. The mapping phi is a bijection and in involution. We recently, together with Alexander Masley and Leonid Shalaginov, we found the following properties of this mapping phi. Let gamma be an element from the set q minus 1, where gamma equals x plus y alpha for some x and y from fq, then the following statements hold. First, f phi of gamma equals y over x minus 1 multiplied by alpha. And second, the set q minus 1 is mapped to the imaginary line alpha fq by phi bijectively. So all points of the oval q but one, namely the unit 1, are mapped bijectively to the imaginary line by this mapping phi, phi. Further, we have the following proposition and theorem. Let gamma be an element from q minus 1 minus 1, where gamma equals x plus y alpha for some x and y from fq, then the following formula holds: phi of gamma squared equals x over yd multiplied by alpha. And the theorem is as follows. Let Q0 be the set from theorem 8. Theorem 8 was about the Q construction, the construction based on the oval Q with the sets Q0 and Q1. Let Q0 be the set from theorem 8. If Q is congruent to 1 modulo 4, then phi of Q0 coincides with the maximal co-clique from theorem 7. That is, phi of Q0 is 1, and the intersection points introduced on that slide, on the corresponding slide. If Q is congruent to 3 modulo 4, then phi of Q0 union 0 coincides with the maximal clique from theorem 7. That is, a phi of Q0 union 0 is equal to the set plus minus 1 and the intersection points introduced on the slide with theorem 7. Thus, what do we have? We have a mapping that preserves the maximal sets or cliques, co-cliques or cliques. It is not an automorphism of the whole graph, but it preserves the objects. It preserves the objects from two different constructions, and this is its advantage. Let me repeat it again, that this is not an automorphism of the whole graph.
So you mean that this correspondence preserves cliques and co-cliques?
In the case of Q congruent 1 modulo 4, it preserves co-cliques.
Mm-hmm.
In the case Q is congruent to 3 modulo 4, it preserves cliques.
I see.
But you mean it preserves the clique, a particular type of cliques, right?
There are two types. We have two types of cliques.
Yeah.
It just sends the cliques of the second type based on oval, objects of the second type based on the oval to the objects of the first type, Baker et al. Type. So our goal is to also we know that the two constructions are not equivalent under the action of the full automorphism group. Our goal is to establish at least some correspondence between them, and we will do this in an algebraic way. So the explanation will be a bit later.
How close phi is to an automorphism?
Okay, let me show my cards. Phi phi is the automorphism of the subgraph induced by the neighborhood of 1.
I see.
Yeah. Okay, thanks.
In a similar way, we can establish a correspondence psi in terms of phi between the other two instances, and we have a very it has similar properties. This correspondence alpha gamma plus d over gamma minus alpha can be written in this way in terms of phi, and the property is that the set, the multiplied over Q by alpha minus alpha is mapped to the subfield of Q by psi bijectively. And we have a similar correspondence. Let alpha Q0 be the set from theorem 9. Let Q is congruent, if Q is congruent to 1 modulo 4, then psi of alpha Q0 coincides with the maximal clique from construction 6, that is from theorem 6, that is psi of alpha Q0 is equal to this. This is alpha Q construction, the set from alpha Q construction. And if Q is congruent to 3 modulo 4, then psi of alpha Q0 union 0 coincides with the maximal clique from theorem 6, that is this, plus minus alpha Q1, so 1 CQ minus 1 over 2. Let us give comments. Although we had established a correspondence between the construction by Baker et al. And our construction based on the oval and showed that these constructions are related, our results were not enough to conclude that the constructions are equivalent. Indeed, as we discussed, these constructions are not equivalent under the full automorphism group. At this stage, private communication with Andres Brouwer helped much. He recognized in the established correspondence phi an automorphism of the subgraph P of Q squared induced by the first neighborhood of the vertex 1. In 2000, Brouwer studied locally Paley graphs, that is, graphs in which the first neighborhoods of vertices induce a Paley graph of the same size, and he reduced the problem of their determination to the problem of finding the automorphism group of the local subgraph of a Paley graph, and showed that if the automorphism group of a local subgraph as he supposed, then a locally Paley graph is either the Taylor extension of a Paley graph or one exceptional graph, namely the complement of 4 times 4 lattice. Later, Muzachuk and Kovac confirmed that the automorphism group of a local subgraph in a Paley graph is as Brouwer supposed. Let gamma q denote the Paley graph of square order P of Q squared, where Q is an odd prime power. Let delta equals a gamma Q of 0 be the subgraph induced on the neighbors of 0. For Q greater than 9, the automorphism group of delta is twice large as the stabilizer of 0 in the automorphism group gamma Q, since also gamma sent to gamma inverse is an automorphism of delta. This is the root of the stated correspondence. Indeed, since finding cliques is something that happens in the local graph, the linear fractional transformation acts. We have the following: phi of gamma is equal to gamma plus 1 over gamma minus 1, and it can be obviously written as 1 plus 2 over gamma minus 1. This shows that the correspondence phi is nothing more but the automorphism gamma to 2 over gamma of gamma q of 0 additively shifted by 1. This shift gives an automorphism of the subgraph gamma q of 1 in P of Q squared induced on the neighbors of 1. This subgraph is isomorphic to gamma q of 0. Thus, the two known constructions of maximal cliques of size q plus r of q over 2 in P of Q squared are equivalent. This means the statement of conjecture 2 is an exact analog of the Hilton Milner theorem, and it was noted by Chiho Ip in our private communication. Since Paley graphs are vertex transitive, the problem of determination maximal cliques of size t in them can be reduced to the problem of determination maximal cliques of size t minus 1 in the subgraph induced by the neighborhood of any vertex. Note that the number of orbits on maximal cliques in the local subgraph can be larger. On the other hand, if we know the graphs that are locally Paley graphs, and we do know, due to the nice works by Brouwer and Muzychuk and Kovac, then the problem of determination maximal cliques of size t in Paley graphs can be reduced to the problem of determination maximal cliques of size t plus 1 containing a given vertex. And these cliques are of size t plus 1 are considered in the locally Paley graphs. Further, we discussed the structure of the characterized locally Paley graphs. We know what are locally Paley graphs. A graph gamma is said to be locally X, where X is a graph or a class of graphs, when for each gamma from from capital gamma, the subgraph induced by the neighborhood of gamma is isomorphic to, or respectively, a member of X. An antipodal graph is a connected graph gamma of diameter d greater than 1, for which the graph gamma d, that is the graph on the same vertex set with two vertices being adjacent whenever they are at distance d, is a disjoint union of cliques. The folded graph of gamma is defined as the graph gamma bar whose vertices are the maximal cliques of gamma d, adjacent if their union contains an edge of gamma. If in addition each vertex gamma has the same valency as its image under folding, so that in particular d is greater than 3, then gamma is called an antipodal covering of gamma bar. Know that the folding map will be a local isomorphism, precisely when d is greater than 3. If moreover all maximal cliques of gamma d have the same size r, gamma is also called an antipodal R cover. Double cover if r equals 2, triple cover if r equals 3 of gamma bar. A distance regular graph gamma with intersection array k mu 1 mu k is called a Taylor graph. It follows, it is known, this is the reference, that such a graph is an antipodal double cover of the complete graph k with k plus 1 vertices, where k is given by the intersection array. The local graphs delta of a Taylor graph are known to be strongly regular and satisfy these conditions. In particular, k is mu multiplied by 2. K equals 2 mu in this local strongly regular graphs. Given a graph sigma with vertex set x, its Taylor double is the graph with vertex set x epsilon, where x runs over x and epsilon is plus 1 or minus 1, and edges x delta y epsilon for x not equal to y, with the property that if x is adjacent to y in x, then x delta and y epsilon are adjacent in the Taylor double if and only if delta epsilon is 1. And if x is not adjacent to y in x, then x delta and y epsilon are adjacent in the Taylor double if and only if delta epsilon is equal to minus 1. Given a strong irregular graph delta with the property k equals 2 mu, its Taylor extension T delta is the Taylor double of the graph delta together with connected with some specific vertex called the vertex at infinity. So this is the cone. So this means that we connect this special vertex denoted by infinity with all the vertices of delta. It is a Taylor graph. That the Taylor extension is always a Taylor graph. Proposition 4, it can be found in the book by Brouwer, Cohen, and Neumeier, and for an explicit proof, you can see this PhD thesis. It is in French. The Taylor extension of a Paley graph is vertex transitive and thus is locally Paley. And the statement, the Brouwer's characterization obtained with the help by Muzachuk and Kovac reads as follows: a locally Paley graph is either the Taylor extension of a Paley graph or the complement of 4 times 4 lattice. This slide provides the description of so-called Meton distance regular graphs. Let Q equals Rm plus 1 be a prime power where R is greater than 1 and either M is even or Q is a power of 2. Let V be a vector space of dimension 2 over the field of Q provided with a non-degenerate symplectic form B. Let K be the subgroup of the multiplicative group F star of index R, and let B be any element of F star. Then the graph M of MQ with vertex set consisting of the sets KV, where K is the subgroup and V runs over all the vectors from V minus 0 with two sets KU and KV being adjacent if and only if the value of the form B of UV belongs to the set BK. This graph M of MQ is distance regular of diameter 3 with R plus Q plus 1 vertices and the following intersection array: Q, Q minus M minus 1, 1, 1, MQ. These graphs are known as Meton graphs. Proposition 5. The Meton graphs with parameter R equals 2 are isomorphic to the locally Paley Taylor graphs from Brouwer's classification. Thus, all locally Paley graphs have a nice algebraic description. So we don't need to consider the Taylor doubles explicitly. We can just refer to the corresponding special case of Meton graphs. In 2022, Brouwer made the I know this from private communication. He made the following computations. He counted the number of orbits on the maximal cliques of size Q plus R of Q over 2 plus 1 in the Taylor extension of P of Q squared. But not all maximal cliques, but only only those that contain a given point, a given vertex. If Q equals 9, 11, 13, 17, 19, and 23, then there are more than one such maximal clique. But whenever Q is greater than 25 and less, greater or equal to 25 and less or equal to 47, Brouwer's computations show that the Taylor extension of P of Q squared contains a unique under the action of the full automorphism group maximal clique of size Q plus R of Q over 2 plus 1. And the following conjecture is thus equivalent to conjecture 2. Conjecture 2 is the proposed statement of the possible analog of the Hilton Milner theorem. Conjecture 3. For Q greater or equal to 25, the Taylor extension P of Q squared contains a unique under the action of the full automorphism group maximal clique of size q plus r of q over 2 plus 1, and this clique is second largest.
What is the largest one?
The largest one, since this graph is locally Paley graph,
yeah,
and we know what are the largest cliques in the Paley graph. It was discussed in the first lecture. These are the canonical cliques, and the nature and the structure of the Taylor extension that we extend neighborhoods which are Paley graphs by additional vertex. So if we combine the canonical cliques in Paley graphs together with this additional vertex, we get the resulting maximum cliques in the Taylor graph of size q plus 1.
I see something.
Let us give some comments.
So the equivalence of two conjectures, this come from 2-to-1 correspondence of orbits because of the the automorphism group twice larger.
The key point of Brouwer's proof is that locally Paley graphs, I mean, their properties and their classification is related to, he reduced this problem to the problem of investigation of the automorphism group of the local subgraph. And he indeed first observed this linear fractional automorphism, and he recognized his automorphism in the correspondence we established last year.
Okay. Thanks.
Let us give some comments. So we expect an exact analog of the Hilton Milner theorem for Paley graphs of square order when q is greater or equal to 25. Despite that many experts have looked into this conjecture, little partial progress has been made. If you are interested in this problem and would like to take part in this project, please let me know. I would be happy to share all my knowledge, and your help will be much appreciated. According to computations, a conjecture similar to conjecture 2 can be formulated for a subclass of Peis graphs. The rest of this lecture is devoted to a brief discussion of Peis graphs. In 2001, Peis gave a full description of self-complementary symmetric graphs and their automorphism groups. In particular, he proved that apart from the Paley graphs, there is another infinite family of self-complementary symmetric graphs, now called Peis graphs, and in addition, one more graph not belonging to any of these families. The Peis graph of order q, where q is equal to p to the power of r, p is a prime power such that p is congruent to 3 modulo 4 and r is even, denoted by p star of q, is the Cayley graph over the additive group of the finite field fq, where the connection set is given by all the elements g to the power of j, where g is congruent to 0 or 1 modulo 4, where g is a primitive root of the field fq. So the only difference with the definition of Paley graphs is that for Paley graphs, j must be congruent to 0 or 2 modulo 4, but for Peis graph, j is congruent to 0 or 1 modulo 4. It can be shown that a Peis graph p star of q squared is a Peis type graph if and only if q is congruent to 3 modulo 4. Equivalently, if and only if the subfield fq forms a Dressard clique. Thus, if q is congruent to 3 modulo 4, canonical cliques are well defined for the Peis graph p star of q squared. And we can ask what are the corresponding Erdős-Karada properties. In 2009, Mullin a PhD student of Chris Gotzel conjectured in her, that time she was a master's student, and it was in her master thesis. She conjectured that if Q is congruent to 3 modulo 4, then the Peis graph with order Q squared has the strict EKR property. Recently, in 2022, Shamil Asgarli and Chihua Ib confirmed this conjecture when Q is equal to P to the power of n and P is strictly greater than 8.2 multiplied by n squared. The construction of the clique, supposed to be second largest maximal clique, is simple and similar to what we had in the case of Paley graph of square order. Note that the subfield FQ is a maximum canonical clique in the Peis graph P star of Q squared, where Q is congruent to 3 modulo 4. Pick an element X from the difference FQ squared minus FQ and consider the clique C consisting of the vertex X and all the vertices from CX, where CX is the set of neighbors of X in FQ. Note that C has size Q plus 1 over 2. And let us formulate conjecture 4. Let Q be an odd prime power. Q is congruent to 3 modulo 4. Then C is the second largest maximal clique in the Peis graph P star of Q squared. Moreover, if Q is congruent, if Q is greater or equal to 23, this clique is unique among maximal cliques of this size under the action of the full automorphism group of the Peis graph. The existence part and the maximality part of conjecture 4 has been computationally checked for Q equals 7, 11, 19, 23, 27, 31, and 43. The uniqueness part has been computationally checked for Q equals 23, 27, 31, and 43. It is clear that the statement of conjecture 4 is an exact analog of the Hilton Milner theorem for special class of Peis graphs. This analog is even more exact than the one for Paley graphs of square order, since we have only one general case which exactly corresponds to the original Hilton Milner theorem, because we do not have an extra vertex in the maximal clique as we do in one of the cases for Paley graph of square order. Let me also give some comments, some relation between the Taylor extension and Gotzel-Mackay switching. Lemma 1, let gamma be a stronger regular graph with the property k equals 2 mu, so that the Taylor extension can be taken, then the following statements hold. For any vertex gamma, from gamma, the switching edges between the first and the second neighborhoods of gamma can be viewed as a Gotzel-Mackay switching with respect to the following partition. C1 consists of, just of gamma. C2 it consists of the vertices from the first neighborhood of gamma, and the rest set D consists of all the vertices of the second neighborhood of gamma. And thus, such kind of switching between the edges of the first and the second neighborhoods of gamma results in a strong regular graph with the same parameters as gamma. And second point is that the Taylor extension of gamma is locally gamma graph if and only if, for any vertex gamma, the switching edges between the first and the second neighborhoods of gamma results in a graph isomorphic to the original graph gamma. Note that the Taylor extension of a Paley graph is locally Paley graph. So this means that it was shown that in different terms, in another language, that the Gotzel-Mackay switching between the first and the second neighborhood of a vertex in a Paley graph results in a graph isomorphic to the same Paley graph. Problem 3. Let us formulate problem 3 and two more conjectures. If is there a pseudo Paley graph gamma or just a conference graph gamma different from a Paley graph such that the Taylor extension of gamma is a locally gamma graph? And we made some computations, and we thus formulate the following two conjectures. Taylor conjecture 5: the Taylor extension of a Peis graph is not locally Peis graph and thus is not vertex transitive. Conjecture 6: the Taylor extension of a Peis type graph gamma different from a Paley graph is not locally gamma graph. And this is my final slide. Let us make concluding remarks. In this lecture, we have discussed two conjectures whose statements can be viewed as exact analogues of the Hilton Milner theorem for Paley graphs of square order and special subclass of Peis graphs. In the next final lecture, we will discuss extremal Peis type graphs without strict EKR property, that is, Peis type graphs having non-canonical cliques and the smallest possible number of canonical cliques. Thank you very much for your attention.
Sergey, thank you very much for this interesting talk. Well, Akihiro, do you have questions? You have already had during this lecture.
Yeah, I have a question in the final slide. I think you mentioned something like switching results in isomorphic graph for the Paley case. So can you repeat that statement?
The statement was as follows: if we take a vertex in a Paley graph and consider two sets, the first neighborhood and the second neighborhood of this vertex, and switch edges between these two neighborhoods, then the resulting graph is isomorphic to the original Paley graph, and this is the root of the phenomenon that we get. I mean, this switching is related to the nature of the Taylor extension, and this is the root why the Taylor extension of a Paley graph results in a locally Paley graph. In most of the cases, I checked the Taylor extension of some graph with k equals 2 mu does not result in a graph that is locally this strong irregular graph with k equals 2 mu, because so at least two neighborhoods are isomorphic. We have two vertices at infinity, but for different vertices we have some non-isomorphic strong irregular graphs.
So you mean by computational results?
Yeah. So I checked. I tried to take the Taylor extension of Peis graphs and some Peis type graphs, that is fusions in amorphic cyclotomic schemes. I mean conference graphs. The Taylor, I did not meet any case except Paley graphs when the Taylor extension is a locally gamma, where gamma is the graph we extend.
I see.
Are you saying that the switching of first and second neighborhood results in the isomorphic graph is equivalent to the Taylor extension locally gamma?
Yeah, it follows from the definition of the Taylor extension.
Okay, so the second statement of the lemma. And I see. And you observe that this happens only for Paley. I mean, do you conjecture that this happens only for Paley?
Yeah. And I'm wondering if there are any locally gamma graphs where gamma is a conference graph different from the Paley graph.
I see.
Okay.
Okay. So no other questions, right? Yeah.
There's one question about computation. I think it's very early part you show some computational experiment. So in the latter part, you have Q from 25 to 40 something, but in the early part, 83 looks
83,
quite, yeah, this looks quite large.
Yeah.
Because the number of vertices is 83 square.
Yeah.
But you check that
So it was done in Magma, and I used the property that Paley graphs are arc transitive. So I to enumerate the cliques, I fixed an edge without loss of generality, and considered orbits in the subgraph induced by the common neighborhood of these two vertices, and then it was some it was difficult to have this result.
I see. So subgraph induced by common neighbor of our edge, it's still several hundred vertices, right?
It reduces the complexity of the computation.
Yeah, still quite large. Yeah. Okay. Thank you very much.
Okay.
Yeah, thank you. Thank you, Sergey. Yeah, it was really very interesting. Yeah, new results, new ideas, conjectures. Okay, but we hope to have some new results in 2 weeks.
Yeah.
Yeah. Okay. Thank you. Thank you indeed. Yeah, it was great. Yeah. Thank you.